My name is Nur Frashasna, and today I will present the introduction and problem investigation for our water and wastewater engineering project. Water is an essential resource for daily life, public health, and economic development. Besides providing clean water, proper sanitation and wastewater management are equally important because untreated wastewater can pollute rivers and spread waterborne disease. Our project focuses on a Kampung Orang Asli community that currently depends on untreated river water for drinking and daily domestic activities. According to the project scenario, the village consists of 100 houses with an estimated population of 500 people. The average water demand is 180 liters per person per day, and around 80% of the water used becomes wastewater. Since the village is located in a remote area with limited infrastructure and electricity, the proposed water and wastewater treatment system must be practical, energy efficient, and suitable for long-term operation. The objective of this project are first to investigate the existing water supply and sanitation issues. Second, to propose suitable water treatment and wastewater treatment systems. Third, to evaluate the sustainability and feasibility of the proposed systems. Problem investigation. From our investigation, the main issue is that the community relies on untreated river water. Although the river is easily accessible, the water may contain suspended solids, microorganisms, and other pollutants, making it unsafe for direct consumption. To ensure safe drinking water, the proposed treatment system follow the WHO guidelines and MS 1228-2023. The key water quality parameters include pH, turbidity, and E. coli, which must meet the required standards before the water is supplied to the community. Using untreated river water can expose the community to diseases such as cholera, dysentery, and typhoid fever. Therefore, an effective water treatment system is essential to improve public health, protect the environment, and provide a safe and sustainable water supply. In conclusion, this investigation highlights the need for a reliable water supply and wastewater treatment system to improve the quality of life of the Kampung Orang Asli community while supporting sustainable water management.
Good day to the panel. Today I am going to present our design for a water treatment plant tailored for a Kampung Orang Asli community with a population of 500 people. The primary objective of this project is to provide a sustainable, safe and regulatory compliant water supply system. Based on SPAN standard, the per capita consumption rate is set at 180 liters per person per day. From this baseline, the average daily water demand is calculated at 90 cubic meters per day, which equates to an average flow rate of 1.042 liters per second. Factoring in a peak hour factor of 2.5, our peak water demand reached 2.6 liters per second. For the sanitation network, applying a wastewater return fraction of 80%, the system generates a daily wastewater volume of 72 cubic meters per day. The average wastewater flow stands at 0.833 liters per second, while the peak wastewater flow hits 2.08 liters per second. All values strictly comply with SPAN, MS 1228, MS 1229 and WO guidelines. To ensure high engineering feasibility, our design parameters have been successfully validated against typical design criteria. The coagulation rapid mixing tank utilizes a 2-minute detention time with a 3-meter water depth. The flocculation basin operates at a 30-minute detention time with a standard 2:1 length to width ratio. The sedimentation tank features a surface overflow velocity of 30 meters per day and a 3:1 length to width ratio. Our rapid sand filter is optimized at filtration rate of 5 meter cubic meter square hour, utilizing a 0.60 meter sand depth and a 0.30 meter gravel depth. Lastly, the chlorination tank guarantees a 30-minute contact time at a 3-meter depth. Every single unit achieves an acceptable status against industry guidelines. In conclusion, this conventional treatment plant is technically reliable, cost-effective, and fully optimized to deliver safe drinking water while supporting UN Sustainable Development Goals 6 and 14 for the community. Thank you.
Water treatment plant design. The proposed system uses a conventional water treatment process because it is reliable, economical, and suitable for a rural community such as Kampung Orang Asli. The treatment process starts with river water as the raw water source. First, the water passes through an intake structure and core screen to remove large debris such as leaves, branches, and plastic. Next, coagulation and flocculation are carried out. Chemicals are added to help small suspended particles combine into large flock. The water then enters the sedimentation tank where these flocks settle at the bottom. After that, the water passes through a rapid sand filter to remove remaining fine particles. Then, chlorination is applied to kill harmful microorganisms and ensure the water is safe for drinking. Finally, the treated water is stored in a storage tank before being distributed to the community. This conventional system is technically reliable, economical for rural community, and easy to operate and maintain.
My name is Dayan Siti Nur Aisa. I will present our engineering design calculation for a primary rectangular sedimentation tank. First, our design centered around a small community with a design of population 500 people. To estimate the flow, we use a standard baseline water demand of 180 liters per person per day. We assume that 80% of this consumed water actually leaves household as osmotic wastewater and enters our drainage network. Let's step through the flow map. First, we calculate the average daily wastewater flow. We multiply our population of 500 by the water consumption and our 80% generation factor. However, we cannot design treatment infrastructure based solely on average. To accommodate peak hour surge, we multiply our average flow by our peak factor of 2.5. This yields a peak design flow, which translates to 179.8 cubic meter per day that our tank must be structurally capable of handling. To wrap up our engineering design, we ran two critical hydraulic verification checks to ensure our dimensions comply with industry regulation. First, we check the peak overflow rate by dividing our peak flow by our actual surface area. Because standard regulation allow a peak range between 60 and 120 meters per day, our design safely passes. Second, we check our hydraulic detention time at average flow, dividing our 6 cubic meter tank. This falls perfectly in line with standard guidelines, providing enough for a solid to settle without letting the water sit so long that it becomes septic. In conclusion, our proposed primary sedimentation tank design for this 500% community proves this setup functions safely and optimally under both average and peak hydraulic conditions. This poster illustrates the step-by-step wastewater treatment process designed for a rural village of 500 people, which manage an expected effluent output of 72,000 liters per day using an efficient aerated lagoon system. The clean water journey begins with preliminary bar screening and grit removal to trap large debris and sand, followed by primary sedimentation, where heavy solids sink and fats rise to reduce the overall organic load. Next, the water undergoes biological purification in an aerated lagoon, where mechanical aerators supply oxygen to microorganisms that decompose biodegradable matter. Finally, the water passes through secondary clarification to separate remaining biological sludge and is treated with a regulated amount of chlorine for disinfection before being safely discharged into the river in compliance with DOE standards to protect the aquatic system.
From the aspect, the proposed system helps reduce river pollution and protect the surrounding ecosystem by ensuring wastewater is properly treated before discharge. From the social aspect, access to clean and safe water improve public health, prevent waterborne disease, and enhance the quality of life of the Orang Asli community. From the economic aspect, the proposed treatment system have lower construction and operating costs, requires simple maintenance, and can be expanded in the future if the population increase. Overall, the design support SDG 6, which is clean water and sanitation, and SDG 40, life below water, making it a balanced and sustainable solution. In conclusion, the proposed water supply and wastewater treatment system successfully address the current water and sanitation issue faced by Kampung Orang Asli community. The design provides safe drinking water, protect the environment, improve public health, and reduce pollution. In addition, the system is practical, cost-effective, easy to maintain, and suitable for rural areas with limited infrastructure. Therefore, this project offers a sustainable and long-term engineering solution for the community. Thank you.